You should replace it now then. Replace it now since this is a break.
I
Want to stop again.
want to take a minute out, more than a minute, out to talk about another homework problem that was due for today. Because I feel like it ended up that the homework problems that I assigned for today were all of the, you do the problem and you look at it and you go, how could that be? Ooh. And it's neat and it's surprising, and it explains actually why we build some devices the way we do. And so the device that I want to talk about right now was a homework problem, which was the toroid. So I have, and it's only really neat in approximation, but the approximation is a very good approximation. So you have a coil, and I won't draw them all, a wire that just sort of goes around like that, right? And I'm going to drive current through this wire so that in here the current flows in, and out here the current flows out, right? So it's going in on the coil of wire there and back out, so it's constantly in and out. And if we were to view this edge on, then that's sort of going to look like that, sort of. Okay? So in order to analyze this, I'm probably going to drop a C and a pi up here somewhere. Oh, I do have it over there. I can use Ampere's law. Why would I use Ampere's law? Because I have high symmetry in the problem. I can identify a path over which the magnetic field will be constant. Equals 4 pi over C integral over the surface enclosed by that path of J dot dA. Right? What this really is the current enclosed by the path. Right? So we're interested in the magnetic field. Actually, we can find it in all regions. Let's start out here. I want to find the magnetic field in this region on the inside. What I'm going to do is take a path that's, actually doesn't matter where it is, but for the moment I'll take it in a plane that crosses right down through the center there. Right? I'll take that path and I'll choose a path that starts here and goes around like so, so it goes inside all of the current in the problem. I can argue by the symmetry that the magnetic field here must be equal in magnitude to the magnetic field here, and it must point in a circular direction. And therefore, I can conclude, since B times 2 pi r being the distance from the center, is equal to the current enclosed when the current enclosed is 0, that the magnetic field is 0 inside. Right? I can likewise go outside and conclude that the magnetic field is 0 on the outside. There's a little bit of a cheat here, and I will be curious to know who caught the cheat in a minute. Right? There's a little bit of a cheat here, but the argument can be made that the magnetic field has to be outside because the net current flowing through this surface that I just chose down the middle here has got to be 0 because what goes in goes out. All right? So I know that my magnetic field is 0 out here and 0 in there. Now I come to the inside the torus itself, and the current that flows through that surface is equal to the number of turns times the current in each turn in the coil. So I have V times 2 pi r is equal to 4 pi over C times the number of turns in the torus times the current in the coil. Do that right?
Yep.
Okay. And so the magnetic field is pretty simple in the torus, right? It looks like 4 pi over c, and oops, 2 over c n I r. That's it, right? What's sort of neat about that is that actually that's the magnetic field here as well. And here, everywhere in the torus, the magnetic field is described by that, because I can always find, here's the current that's enclosed by the loop that I just drew, right? So the magnetic field is independent of vertical position in the torus. And I found that when I first did that, when, you know, I think probably the professor assigned it to us and said, find the field as a function of position here. And I probably stared at it for an hour, wondering what the trick was. There was no trick. The magnetic field is independent of the height. And by the way, it doesn't matter what shape the torus is.
It's not a torus.
Okay. It
Square
could,
torus.
yeah, it could be a torus with a square cross section, or a triangular cross section. Whatever you like, it's going to be the same. As long as the magnetic field can be a constant around the loop. Yeah.
By the way, were we supposed to find it outside? The problem didn't say.
No, I'm just mentioning that you could. All right, so where was the cheat there? One of you I know caught that and asked me about it.
When you're wrapping the wires, they're not going straight up and down,
Right.
so they actually will create a net.
There actually is a current flowing around the torus in that direction, because it's a helix. Well, it's not even a helix, but the wires are making a path around. So there actually is a net current flowing around this way, right? And we should include, well, of course, that doesn't pass through that surface, but it will give us a magnetic field in and out. So it's not really zero on the inside and on the outside.
But we curled an infinite solenoid into a loop.
Did we?
Definitely.
Oh.
How?
I'm not sure how you,
Why
how
don't
you
we
curl
think
an infinite solenoid into.
they find
Then it
out?
has no radius of curvature.
Yep.
So I thought that was neat, and that has a neat application as well.
So great.
And it explains why we use toruses.
And now I'm gonna